Previously, we discussed mixing problems where the governing differential equation is derived using a basic balance principle or a basic conservation principle. And what we want to do here is that we want to look at another example, water leaking through a hole at the bottom of a tank. In this example, we can also derive the governing equation by considering a simple balance principle, a simple conservation principle. All right, let's dive in. Let's see what our example looks like. Consider a tank. We have our figure to the right. This purple object is our tank. Consider a tank with a height of h and a horizontal cross-sectional area A of y at height y. As you can see, we are assuming that the cross-section it depends on the height. As height changes, the cross-sectional area may change, and our symbol for the cross-sectional area at height y is A of y. It depends on the height y, okay? The tank is filled with water, and water drains through a hole of area B at the bottom of the tank. So at the bottom of our tank, we have a hole here at the bottom, and the water is draining, as you can see here. The area of this hole that we have at the bottom is equal to B. Awesome. So what do we want to do here? Let y of t represent the water level at time t. Set up a differential equation for y of t. Obviously, the value of y of t is becoming smaller as time goes on, right? The water is draining from the bottom of the tank. So the expectation is that this y of t is a decreasing function of time. And we want to come up with a differential equation for finding y of t. And there is another hint in the statement of the problem. It says that you may use Torricelli's law from fluid mechanics, which says that the velocity of water leaving the hole when the tank is filled to the height y is given by v equals negative square root of 2gy. This g is the acceleration due to gravity. We saw it in several of the previous problems. We solved 9.8, approximately 9.8 meters per second squared. Awesome. So we know the velocity of the water as it is leaving this hole at the bottom of the tank. We want to derive our differential equation for y of t. And like I said, our derivation will be based on a very simple conservation law, very simple balance principle. So let me write that. Our derivation of a differential equation in this problem governing y of t, the water level at time t, will rely on a straightforward balance principle. Conservation principle. And again, as soon as I write the conservation principle, you will see that it makes perfect sense. Also, again, I recommend that you go back to our introductory videos, look at the discussion that we had about sources of ODEs. One of the sources for many ODEs that appear in modeling real-world problems is this conservation principles, which are actually very simple to understand. So what is the conservation principle? On the left, the change in the volume of water in the tank over the time interval from t to t plus delta t is equal to, equals on the right. So let me actually put this inside parentheses, this quantity. This is equal to the amount of water, the volume of what by amount here I mean volume, the amount of water entering the tank during that interval, the interval from t to t plus delta t. The volume of water entering the tank from t to t plus delta t minus the amount of water, the volume of water, that to be very specific, the volume of water leaving the tank, leaving the tank in the same time interval, during the same interval. So this equality should make perfect sense. This is our conservation principle here. I'm gonna call this 1. We will be using this equality later. So this is equality 1 in order to come up with our differential equation. Now my job is to come up with mathematical expressions for each of these quantities that you see in this equality. What we have on the left and the terms that we have on the right. Let me give a name to these guys. I'm gonna call this 1. I'm gonna call this guy 2. 2 is the easiest. The volume of water entering the tank. In this problem, it's 0. So I will come back to this. But immediately you know that based on the description of the problem, the amount of water entering the tank is equal to 0. And then I'm gonna call this 3. One by one, we will study these quantities and we will come up with mathematical expressions for them. So starting with 1, the change in the volume of water in the tank from T to T plus delta T. So I'm going to focus on 1. So what we have here, let me draw our tank. Here we go. This is the tank. And let's say that at time t, the water level is y of t, and water is draining from the bottom. So at time t plus delta t, the water level will have a smaller value, y of t plus delta t. And this will be, okay, this shaded region is the volume of the change in the volume of water. The volume of this segment is the change in the volume of water during the over the time interval from t to t plus delta t. So this is what we want to compute. The volume of this shaded region, the change in the volume of water in the tank over the interval from t to t plus delta t. So let me actually write this. This volume is the change in the amount of water in the tank between T and T plus delta T. And again, remember, ultimately, we will take the limit as delta t goes to 0 in order to come up with a differential equation. So keep in mind that ultimately this delta t is going to be a very, very small number, and we will take the limit as delta t goes to 0. So what I'm going to do is that I'm going to use those techniques that I talked about in our introductory videos to approximate this volume based on the knowledge that ultimately I'm going to send delta t goes to 0. So I'm going to write for very small delta t, eventually we will let delta t go to 0 when we want to come up with our differential equation. So we will not making like a claim that is unjustified. Ultimately, we will let delta t go to 0. So what we are interested in is the case where delta t is very small. This volume, the volume of the shaded region, this volume can be approximated by, so let's think about it. My friends, this cross-sectional area on top, the cross-sectional area on top, our notation for it was A of y of t. When the water level is y of t, the corresponding cross-sectional area, we write it as A of y of t, the A that corresponds to the height y of t. The cross-sectional area on the bottom is A of y of t plus delta t, where the height is y of t plus delta t, and the corresponding cross-sectional area is A that is associated with this height, y of t plus delta t. However, since delta t is very, very small, and I can consider the change, I can approximate this continuous function cross-sectional area with its value on top with a of y of t. I see that, yes, the cross-sectional is changing as the height changes from y of t to y of t plus delta t. But since delta t is very small, and ultimately I want to send delta t to go to 0, I can assume that this change is very, very small. I'm going to approximate the value of the cross-sectional area by the value of the cross-sectional area on the top, which is A of y of t. That means that I'm going to approximate this shape with a cylinder, with a fixed cross-sectional area, A of y of t. Again, I recommend everyone to carefully go over those introductory videos. One of the items that I discussed was exactly what we did here. All right, this volume can be approximated by the volume of a cylinder of height y of t minus y of t plus delta t and base A of y of t. So this is what I'm doing. I'm considering this cylinder. Here we go. The height is y of t minus y of t plus delta t. And the base is A of y of t. All right, excellent. So what is now the conclusion? Obviously, the volume of the cylinder is the area of the base times height. So the conclusion will be as follows. Volume of water in the tank at time t plus delta t minus volume of water in the tank at time t is approximately equal to, this is the change in volume, and it will be a negative number because water is draining. So at time t plus delta t, with the volume of water will be less than the volume of water at time t. So this is negative times the volume of this shaded region approximately, and this approximation becomes better and better as delta t goes to 0. Negative height times the area of the base, A of y of t. Let me give myself a little bit more space. A of y of t, which is area of the base. This approximation becomes more accurate as delta t goes to 0. Let me also write that. This approximation becomes more accurate delta T becomes smaller and smaller. Awesome. So that was quantity number one. I talked about quantity number one. And let me actually give a name to this result because I'm going to use it later. I'm going to call this equality that we just discovered together 2. All right, let me change the scale for this page so that I can see everything we have. All right, excellent. Now I'm gonna focus on this second, the green quantity in our formula, the amount of water entering the tank during the interval. And this one, the easiest, 0, 0. So quantity number 2, I know that it is 0. According to the statement of problem, there's no water entering the tank. So 2, this one is easy. The volume of water entering the tank between T and T plus delta T is equal to 0. So let's call this conclusion 3. And then finally, this red quantity that I have in my conservation law, the volume of water leaving the tank during the same interval. So let's think about that. Let me focus on this quantity now, the red quantity, 3. Now we want to focus on the red quantity. So this is our tank. All right. We have a hole here of area B, and the water is draining through this hole. This is the water coming out of the hole. As you can see, at least for a small delta T, the volume of water that is exiting the tank, it forms a cylinder. What is the base, the area of the base of this cylinder? It is given to us. It is B. That number is given to us. What is the height of this cylinder? The height of the volume of water that left the tank during the interval from T to T plus delta T. So think about it. If we assume that the velocity of water leaving the tank is V, after delta T seconds, the particles that were here at the bottom of the tank, after delta T seconds, they will move V times delta T units, right? So after delta T seconds, we will have a cylinder of height V times delta T. Here I'm talking about the magnitude of velocity. Everything is a positive number here. Magnitude of velocity times delta T. So what we have at the bottom is equal to V times delta T, assuming that the velocity with which the particles are, the fluid particles, the water particles are leaving the tank, it's constant, right? Of course, there is a point here that we need to be careful about, and I'm going to be very careful about it. So it seems that the volume of water leaving the tank will be like a volume of a cylinder of base B and height V delta T. I'm going to be a little bit more careful about this because this V, we have to be careful. This V, the velocity is changing with time. Let me scroll up. According to the Torricelli's law, velocity is square root of the magnitude of velocity is square root of 2gy. This y itself, it is the water level in the tank. It is changing with time. So V, the velocity that the fluid particles are leaving the tank, with which the fluid particles are leaving the tank, that is also changing with time. It's not a constant number. It depends on y. So I'm going to be careful about my argument here. So let me write the careful argument here. And again, everything goes back to those techniques that I told you we use in modeling ODEs in the introductory videos. So again, I'm going to use the fact that this delta T is very small. And ultimately, I'm going to take the limit as delta T goes to 0. We note that, so this was our tank. We note that for very small delta T, and again, remember that ultimately we're going to take the limit as delta T goes to 0. The water exiting through the hole between t and t plus delta t over the time interval from t to t plus delta t forms a cylinder, this green cylinder that you see here, of base V, there is no question about the base, and height approximately, so this is the part that now I'm being careful about. I'm not saying that exactly, approximately equal to V corresponding to the height at time t times delta t. So this V is changing with the water level. As little t is changing, Y is changing, and so V is changing. So we can talk about the velocity at time t, the velocity at time t plus delta t, the velocity anywhere in between. But since delta t is small, I'm approximating the velocity with a constant function, the value of the velocity at time t. That is what I'm doing. So the velocity with which the water is exiting the tank. So let me also explain what I just said. Since delta t is very small, the exit velocity during over the interval from t to t plus delta t, it is not in reality, it is not a constant function. It changes over this interval, but I'm approximating with it with a constant function. Is approximately equal to V at the left endpoint, Y of this interval. Or and so and this is the consequence, and so the water travels approximately the distance absolute value of V times at Y of t times delta t during this interval. Okay, so this is the distance traveled by the water, which is absolute value of V times delta t, V evaluated at Y of t, V at the time t. All right, so now we have the clear expression for the volume exiting the tank over the time interval from t to t plus delta t. So the conclusion of this argument that we just made is that, let me just do a summary, sum of what we have learned. The volume, so the volume of water leaving the tank between t and t plus delta t is approximately equal to the area of the base. Look at the green cylinder on top. That is the volume we're interested in, times V of y at the time t, times delta t. That V of y times delta t is your height, which is by Torricelli's law. This is B times a square root of 2gy times delta t. Excellent. So I'm gonna give a name to this equality as well. This is equality 4. Okay, 4. So let's go over the things that we have learned so far. We had our conservation law. This is 1. This is what I called 1. And then we separately discuss all the quantities that are appearing in this conservation law. We discovered what we have on the left-hand side. We called that 2. We discovered the first term on the right-hand side. We call that 3. It is 0. And we discovered the second term that we had on the right-hand side. We called it 4. Now I'm going to put all of these things together. And one more time, this, again, notice that this approximation becomes better and better as delta t goes to 0. Let me actually write this. This approximation becomes better and better, becomes better as delta t goes to 0. Oh, so now the conclusion of all of the discussions we had so far. Thus, so we have 1, 2, 3, and 4. All of these together, they will tell us that negative y of t minus y of t plus delta t times a of y of t, the cross-sectional area at height y of t, is approximately equal to 0 water entering the tank minus water leaving the volume of water leaving the tank, b square root of 2gy delta t. This y is a function of t. Let me be very clear about that. Y is a function. The water level is a function of t. Now I'm going to divide both sides by delta t. So what I will get is that y of t plus delta t, I multiply the negative sign with the bracket, minus y of t, divided by delta t times a of y of t is equal to negative b square root of 2gy of t. And I can bring the a to the other side. So y of t plus delta t, approximately equal to minus y of t divided by delta t is approximately equal to negative b 2gy square root of 2gy of t divided by a of y of t. A is a function of y of t. And so by passing to the limit, taking the limit as delta t goes to 0, we obtain. So I'm going to take the limit for on the left-hand side, I will have dy dt. And now since I'm taking the limit as delta t goes to 0, I will have exact equality. And on the right-hand side, I will have just negative b square root of 2gy of t divided by a as a function of y of t. This a of y of t depends on the shape of your tank. The shape of the tank will be given to you. You will be able to compute the cross-sectional area at any height. Okay, b again is the area of the hole. It is given to you. The only unknown here is the function y of t. So this is a first order nonlinear equation for y of t. First order ODE for y of t. ODE for the water level at time t. The unknown is the function y of t. So this was another example, and now we are seeing that these basic conservation principles, balance principles, they can be very useful in deriving ODE models for explaining what's happening in the real world.